Welcome. In this video, we're going to do a brief overview of entropy and what it is. And entropy is a measure of the disorder of a system. And the symbol we use for entropy is S, and this triangle here is delta. That represents change. So if disorder of a system increases, then we say the delta S value is positive. And it turns out that an increase in entropy, or a positive change in entropy, positive delta S, tends to be energetically favorable. So processes that result in an increase in entropy tend to be energetically favorable. They tend to occur spontaneously in nature. There's some examples of increasing entropy is that your room gets messy. This is something that will happen spontaneously, which means like if you just kind of live in your room day to day, it's eventually going to get messy unless you put some effort into cleaning it up, right? But it's spontaneously on its own, it's just going to get messy. Something similar happens with like your lawn. So let's say you don't touch your lawn, you just like let it go for a few months. It's going to become more disordered. You're going to have grass that's at different heights. You're going to have weeds popping up. So that shows how we tend to see an increase in disorder naturally. And the second law of thermodynamics says that the entropy of the universe is going to increase in any spontaneous process. Another example that I find visually helpful for thinking about entropy has to do with making a fruit salad. So the definition of entropy has to do with the different possible arrangements that particles can have. We call those the microstates. So here's an analogy here thinking about making like a melon salad here. So over here initially, we'll call this my reactant side. I've got three possible locations where the melon can be. It can either be in the cantaloupe, in the honeydew, or in the watermelon. But if I make melon balls, if I chop them into pieces and mix them together in a bowl, over here on my product side, I have way more possible arrangements that these melons can take, right, in this bowl. So this would represent an increase in entropy because there's more possible arrangements that the melon can have over here on my product side. And that's what we're going to focus on, is looking at chemical reactions or even physical processes and asking ourselves, did entropy increase or decrease in that process? And entropy, the definition has to do with a number of possible arrangements of particles. We refer to that as microstates. And the entropy, thinking about what zero entropy is, might help us understand what entropy is better. So the definition is the entropy of a perfect crystal at 0 degrees Kelvin is 0. So 0 Kelvin means there's zero kinetic energy, so the particles are not moving around at all. And it's in a perfect crystal. So imagine perfectly orderly, no movement. That is what zero entropy is. And the factors that will affect entropy would be the state of matter of a substance and also the complexity of a molecule. And there's more in your textbook on this. If you'd like to know more detail about what we mean by microstates, there's some other examples, and there's some other videos out there that get into more in depth with what entropy is in here if you're interested. But we don't need to know the theory of this in detail for our chemistry applications. But I will go over a little bit here, thinking about the variables that affect entropy. So state of matter definitely affects entropy. So when the phase changes from a solid to a liquid or a liquid to a gas, the molecules can move around more freely. And when they can move around more freely, there's more possible arrangements, so there's more disorder, more entropy. So for example, with ice, if you go from solid water, which is this very ordered, structured solid here, and you melt it and turn it to liquid water, there's more disorder here, the molecules are moving around more freely. That change is going to involve an increase in entropy. Something else to keep in mind too is that different molecules, like let's say we have two molecules here, they're both gases, notice that their entropy values are different. So it's not just the state of matter that affects entropy, it's actually the complexity of the molecule itself can affect the entropy. And that has to do with the fact that within a molecule, these bonds themselves within a molecule actually do kind of wiggle around. And so there's some possible locations, possible different like microstates that the molecule can have depending upon the number of bonds in it. So the larger, more complex molecules tend to have more possible places for the energy to be. So there's more entropy there. So that's an FYI. Again, you're not going to have to predict the entropy of a particular molecule. So don't maybe worry as much about what's happening on this page, but I just did want to let you know that there are reasons why different molecules have different entropies. It has to do with the complexity of the molecule there. Here are some examples of things that will involve an increase in disorder. So dissolving salt in water, that's going to involve an increase in entropy. And if you think about why, you're starting with this very structured, orderly, crystal lattice here, and then you're mixing it in with water, which water in liquid state, the particles are moving around more freely. We've got way more possible arrangements where these particles can be in the aqueous version. So this is going to involve an increase in entropy. Here's another example looking how melting water will lead to an increase in disorder. In this example, we're showing ice as being like a snowflake. So imagine this very structured, orderly snowflake, and then when it melts, these particles move around more freely, there's more disorder. Here's an overview of 5 things that will cause an increase in entropy in a chemical reaction or process. And one would be if you increase the number of moles. So if you have more particles of products than you do reactants, that's going to give you more possible locations for those particles to be, more possible arrangements. So that's going to cause an increase in entropy. Changing the state of matter will cause an increase in entropy. So going from a solid to a liquid or a liquid to a gas. Going from solid to aqueous will also increase your disorder and increase your entropy. And then increasing the temperature. So remember, we said 0 degrees Kelvin was 0 entropy. So as you increase the temperature, the particles move around more. There's going to be more possible arrangements, more disorder. So that will increase the entropy. All right, thanks for listening.